Okay, this is the last video in my series on vectors. This one here will be the use of components to add vectors. So we'll be adding vectors by use of their components. So this follows along with a handout that I gave out in class that we had to turn in. All the other handouts were notes, and you're welcome to get those notes from your classmates. But the notes are pretty straightforward. They follow the formula chart. We're going to use two formulas for this, and those will become pretty obvious to you in a quick minute. So the first step here is on this particular handout, as you were given two different lines, and these lines needed to be labeled. So you can go ahead and label them A and B, and it doesn't really matter which one is A and which one is B. I've just chosen A and B because this was the first line in the group, and this is the second line because there's the tail of the first one. So this is the original place that the vector starts, and then here's the tail, here's the head, and then it connects to the second one. So I'm going to go ahead and put AX and AY. So I'm going to break down each of these individual vectors, now taking these individually and breaking them down into their X component and Y component. So that means that the component of this vector that moves in the moves in the X direction is going to give me an amount of displacement. So this one displaces 4, and the assignment, I believe, qualifies each box as a centimeter. So this displaces 4 centimeters. So I'm going to put its A of X is 4 centimeters. And in terms of the Y direction, which is up and down, this one does not have any movement in the Y direction. So I will go ahead and label that one as 0. And then get moving to this vector, now treating this individually. Here's the beginning of it and the end of it. So in terms of the B moving in the X direction, it doesn't move anywhere in the X direction, so it's 0. B moving in the Y direction, it moves 1, 2, 3. So it moves 3. So now what I'm going to do is I'm going to solve for the X and the Y components of the result of adding these two vectors. So this is combining them by their components. So first I break them down into their components, and then I add the X component, and I end up with a result, which is the resultant vector for the X component. Add these two together, and I end up with 4. And then the resultant vector for the Y component, add these two together, and I end up with 3. So now what I'm going to do is just go ahead and draw this resultant vector, and we'll draw it in red here, starting back at the original spot where we started this, where the first vector starts. And this vector will, okay, let me get an arrow as far as my shape goes. And again, I'm needing an arrow here. I tell you what, I'll just grab this one already here. This vector will start here, it will rise 1, 2, 3, and it will run 4, just like it says here. So in terms of the Y, it's up 3, X is over 4, and this is what the resultant vector will look like. So then we took that, and that was pretty much all we did on the first day. Right, is we got that, and then we took that, and we solved for the magnitude and the direction of this resultant vector. So right now we just have a picture of the resultant vector, and we have the X and the Y components, the magnitude of the X and the Y component. But what we want to do is solve for the magnitude of the actual resultant vector itself. Right, so there's the magnitude of the X and Y components. Whoops, and what we're going to do here is we solve for the magnitude of the actual resultant vector, this one here. So we want to solve for its length and its direction. So here we go. The formula for solving for the magnitude of the resultant vector is the resultant vector squared is going to be equal to the resultant vector's X component squared plus the resultant vector's Y component squared. This should look very similar because it's basically a version of the Pythagorean's theorem. And then we would go ahead and get rid of the square by square rooting both sides. So we end up with the resultant vectors. The magnitude of the resultant vector can be found by taking the square root of its X component squared plus its Y component squared. And in this case, here's its X and here's its Y. So we would plug those numbers in, and we take the square root of 4 squared plus 3 squared which is going to be 5. So, and again, the formula or the handout tells you that it's a centimeter per box. So the resultant vector is 5 centimeters in magnitude. They always have a magnitude and a unit. And now we're going to solve for the direction of the resultant vector by using another formula, which is theta. So this is the theta value right here, is going to be equal to the inverse of the tan function. So that's second function tan in your calculator, second function tan in your calculator. And then you take the y component over the x component. So when you hit second function tan, it's going to open up these parentheses and allow you to put in this fraction, and you will put in the y over the x. So here I'm going to hit second function tan, and I'm going to hit 3 over 4 and hit my enter button, and what I will get when I do that is, I believe, 37 degrees, which is going to be, so we're going to put this at 37 degrees, and that will be the resultant vector. So that is how you calculate the magnitude and the direction of the resultant vector. I'll do a couple more examples. I'm going to skip ahead a few and go to number 4, and the reason I chose number 4 on this is because this one is a little bit different in terms of it does not, the resultant vector does not end up in quadrant number 1. Instead, this one is in quadrant number 2, and as such, it's handled a little bit differently in terms of the direction. So this one ended up with a Rx value of -5 and an Ry value of 1. So we did this the same way. We broke down this, we labeled this A, we labeled that B, we solved for the component of the A vector and the B vector, and we added the X's and the Y's of the A and the B, and you came up with the Rx and the Ry. And so now we're going to use these in the same formula that we did before, the square root of the -5 squared and the 1 squared. Now, in order to put a negative under a radical, which is the square root sign, you have to put the negative in parentheses and then put the square outside the parentheses. So you put a set of parentheses in, the -5 in, close the parentheses, put the square outside the parentheses, and then your radical will do that function for you. And if you do that for this particular one, you end up with a magnitude of 5.1. So the magnitude of this resultant vector right here ends up being 5.1 centimeters. And then of course we're going to use tan inverse the y, which is 1 over the y over the x, so that's 1 over -5. And when we do that, our calculators return a value of -11. And the reason it does that is because when you look at the x component, see, this is the -5 for the x component, and this is the +1 for the y component. So when you put the x and the y component in place, you see the right triangle that you're actually inputting the numbers, because this is the x and the y component, remember. So this is the y and the y x. So the tan function that you're using is going to return the value for this interior angle. And that interior angle, in terms of its position relative to this western axis, is -11 degrees. Well, we don't need this interior angle. We want, the directions call for us to do everything in standard form. Standard form references everything in terms of the 0 degree axis, so it's a 360 degree circle, so it doesn't break it down into the quadrants. So what we want is, we actually want the complementary angle, and in order to acquire that, you can just add 180 degrees to this negative number, and you will get the correct, you will get this particular angle right here, which turns out to be 169 degrees. So you can report that one at 169 degrees. So that is what it looks like whenever it is in quadrant number 2. Now in quadrant number 3, keep in mind that your angles have to be between 180 and 270 degrees. So you may have to add 360 degrees depending on where you're located. And then in quadrant 4, your angles are between 270 and 360. So again, keeping in mind that you're solving for those interior angles, but what you want is you want the angle, everything reference that 0 position. So you want it in terms of a 360 degree circle. So you will have to work with the quadrant system to determine what angle you're actually, what angle your vector actually is in reference to the 0 degree line. One more thing I want to show you, and that can be found with question number 7 here. So on question 7, when we solve for the x, the r of x and the r of y, we ended up with an r of x of 0 and an r of y of negative 4. So that's why I drew this line here, 0, negative 4. That's my resultant vector. And that does something interesting. In terms of the magnitude of the resultant vector, that becomes pretty straightforward and pretty easy. I mean, you could take the square root of 0 squared plus 4 plus negative 4 squared, put it in parentheses, you get 16. Square root of 16 is 4. You kind of know that because this only has the one axis. So in terms of the magnitude of that, it's going to be 4 centimeters. That's pretty straightforward. But in terms of the direction of this, if you go ahead and plug these numbers into the inverse tan, and then you put the y, which is the negative 4, over the 0, what your calculator will return to you is a big fat error. And the reason is because you have an improper fraction here. You can't have 0 in a fraction. The question is, well, then how do you solve for that? And the answer is, well, you don't solve for it. You memorize it. You have 4 primary axes, the cardinal points is what they're called, and that is the 0 degree. So that is basically north, east, south, or northwest, south, and east. And you're supposed to know these. So this one is 0 and this one is 90, and they're all 90 degree separation. So you add 90 to that and you got 180, and you add 90 to that and you get 270, and you add 90 to that and you get 360 or 0. So those are the cardinal points, and anytime a vector lies on the cardinal points, you can't calculate it, you just have to know it. So you could use 270 degrees. You could also represent this one as south. So you could say 270 degrees, that's your standard form, and that's what the directions actually call for in this particular assignment. But it would be appropriate, if it wasn't calling for standard, to also report this as 4 centimeters at south, because that is pointing straight south. And if it were pointing the opposite direction up, for example, when you get to question 11, it points directly up. So this one is going to be some magnitude, and you can report it at 90 degrees, or you could report it as north, because that's a cardinal point. So the 4 cardinal points, one more time, in your compass is your east, which is 0 degrees, your north, which is 90 degrees, and your south, which is 180 degrees, and your west, or excuse me, your west. I messed this up. This is west at 180 degrees, and this is south at 270 degrees. And so those are your cardinal points. You have to have those memorized. All right, so any other questions on this assignment, let me know, and look for you in my next video.